shared my screen already. You are able to see this Linux only, right? So we'll start with threads today. I have one or two things which is left in process, but in course of time I'll just explain that also. So first here we will start with threads now. So first, if you want to understand threads, here we need to understand something like what is context switching. Okay. Here one concept we have called context switching. Now what is this context switching? Okay. Now we know that it is not executing only one process, right? Even if we see our laptop or our phone, we can just see that we are able to run so many applications at a time or simultaneously, right? We are able to run, right now I am running 3 or 4 applications which is visible to me, these user applications, but internally again it is running so many applications, like you can see in Wi-Fi also, microphone also, everything. These are all processes. So all these applications are executing concurrently, or you can say simultaneously.
Okay.
It is executing one after the other, or it is running concurrently. We need to understand that. Okay. So now it doesn't actually continuously execute only one program. Now if I am using this particular Ubuntu, it is not only executing this process. What it does is this process gets interrupted, or there is a term called preempted. Okay. What this preemption is? Preemption is even though your process is completely executed, the process is stopped or suspended. Okay. Before finishing your execution, process stopped or gets suspended. That is preemption. That means forcefully we are either suspending it or the execution is stopped before the task is finished. Okay. Now why does it do that? Or I can just first we'll see that what is the scenario where this happens.
Okay.
Okay. Now one thing will be like, here we discussed something before that CPU allocates some particular amount of time to process. Right. Suppose if you have 100 milliseconds of time to execute one process, then it will go to second process for 100 milliseconds, then third process for 100 milliseconds. So continuously it will execute like this. Now at this particular task, 100 milliseconds are over, but my task is not finished, my execution is not finished. Then also it will move to next task.
Okay.
It will occur. Because our task, our process has not finished the execution, but process the CPU goes to next process to start the execution. Okay. Why? Because the time which is CPU has allocated expired. It is 100 milliseconds. In 100 milliseconds, I could not execute my whole process. Okay. For this, we need one more term called round-robin method, which we will see now. Now, and one more reason for preemption is interrupt. Right?
Yes.
We have interrupt. So if at all interrupt occurs at that time, what it will do? It will leave that particular process and go and check with that interrupt. We have seen this in 8051 controller also, right?
Yeah.
and one of the interrupt, either it can be high priority interrupts, or one more reason we have called blocking calls. Blocking calls we have seen is your sleep, scanf, wait, etc. Right? Even in case of blocking calls also preemption occurs.
No.
Okay. Now interrupt blocking calls as well as high priority process or task. So the reason for this preemption can be either CPU time expires, or interrupt, or blocking calls, and the last one is your interrupt. Okay. Now here we see this. What happens is, after executing, now suppose you have around three process running at a time. Now in this three process, it is allocating suppose 100 or 200 milliseconds of time. So first 200 milliseconds it is executing first task. Second, it is executing second task. This is my user space of RAM that allocated around 9. With that here I this is my process 1. This is PCB for that particular process. For process 1, this is my PCB. Similarly, this is my process 2, and this is my process 3, and the PCB for process 2 as well as process 3. Now, first, it will start execution from this process 1. After 200 milliseconds, what it will do is, after 200 milliseconds, it will switch it from process 1 to process 2, and it will execute this process 2 for 200 milliseconds, and next it will go to process 3 for 200 milliseconds, and after this 200 milliseconds for P3 is finished, then again it will come to process 1.
Okay.
After 200 milliseconds. Okay. So even though if you finish your task or process in that particular time 200 milliseconds or not, irrespective of your process is finished or not, this process, the CPU will change from one process to another process.
Okay.
Okay. If at all if your process is not finished and CPU has switched it from P1 to P2, you may call it as preemption.
No.
Okay.
Yes.
And these PCBs, they are maintained as nodes. Okay. These PCBs are maintained as nodes, and those are called in a linked list. Okay. This is maintained as linked list. Nodes in a linked list, and this list is called running queue.
Okay.
Okay. And this is maintained by process management subsystem.
Okay.
Because we are managing this particular processing, that which process should be executed. Okay.
Yeah.
Now, who will decide that which process should run next? is done by scheduler.
Okay.
Okay. Now, scheduler is also a program, or you can say it's an algorithm. And here's the scheduler. So who is going to decide this? So scheduler is going to decide this. So scheduler is a algorithm or program, you can say. Algorithm is nothing but a step-by-step program. Which decides, now scheduler is a program which decides which process to run next.
Okay.
And where does this reside? This resides in kernel space of RAM. This is in kernel. Okay, scheduler is in kernel and not in user space of RAM. Okay, now here we have different type of kernels. Sorry, not kernels, sorry, schedulers. We have different types of scheduler programs available. One of it is round robin method, round robin scheduler. Second is your preemptive priority based scheduler. Preemptive. Priority based scheduler. Okay. Now we will see first round robin scheduler. Now here, according to this particular scheduler, every process, whatever how many processes are there, every process gets equal CPU time. Okay, that means if I have 10 tasks, then 10 process, then 10 process will get equal time. Okay, I'll just explain this how this is working. Now, how this works is, suppose this is your CPU. Okay, and I have different process running. So this is my process 1, this is my process 2, process 3, 4, and 5. Now, if your CPU starts executing from process 1, at that time, that after executing process 1, then it will go to process 2. Process 2 to process 3, 4, 5, and then again 1. Okay, so here, irrespective of what is this process, it will allocate only equal time. So if at all, if this is taking 20 milliseconds of time, all the other process will also take 20 milliseconds of time. Okay, this depends on allocation and not exactly if OP process 1 is taking 20 milliseconds of time. This will be allocated by your CPU. Okay, so if at all, if this is like all the process, if at all if it is 20 milliseconds, then all the process will take 20 milliseconds of time. Okay. Now, example, if you take an Intel processor, if you're taking an Intel processor, suppose you say that it is 3 gigahertz processor. You're able to see Ubuntu, right?
Yes.
So if this Intel processor is of 3 gigahertz, at that time, how many cycles it will have? 3 into 10 power 9 cycles. Or if you just convert this, then you may get something like 300 crores of cycles per second. Okay, now if you have these many, that means what? How many instructions? Now if you take your instructions, how many instructions? One, here this is 300 crores cycle per second, but when you say an instruction may take either 1 cycle, 2 cycle, or 4 cycle, anything. So on an average, if we take around 2 cycles also, then on an average, if you take 2 cycles, then 150 crores instructions per second. Right? That means it is able to execute 150 crores of instructions per second. Intel processor, which is of 3 gigahertz. So that's why you will, while selecting your CPU, you will be seeing that how many gigahertz of that processor it is. If it is able to execute these many instructions per second, it is faster. Okay. And we can have around 100 to 1000 context switches within a second. That means within a second it is executing around 1000 processes. If we say maximum of 1000, at that time it can just switch 1000 processes, and again it will come to first context switching. That means if we have 1000 processes, it started from P1 and again it will come to P1 after a second. And that is the reason, even though if it uses RRS also, which is round robin method, as it is executing within 1 second, it is executing this much, we will be feeling like, okay, our application is running concurrently. But they might be it might be like it is executing only one process at a time. Actually, your CPU is executing one process at a time. Okay, but even though it is executing one process at a time, it is doing it so fast that we will not be able to see that it is executing that much. Okay. Now, if you have this context switches at that time, what happens? If you are doing context switches, we will have some CPU registers, right? It's audible, right?
Hello.
It's audible, right?
Yes.
Okay. Now, if you are using some particular processor, at that time we know that our CPU have some registers. Our CPU has some registers like R0 to R15. Then you will have something like stack pointer and program counter. All these registers are there. Even we have these registers in 8051 also. So in depends on how many registers you have. So here you have, if we just assume that you have these many registers, you have only one set of registers. Now if I have 1000 processes, I can't have that many CPU registers, right? So at that time what happens? Here, if at all, if your CPU is executing the first process data will be copied into this. Okay, and when it is executing second, then the second registers, CPU registers contain second process data. Okay, that means it is switching from one register data to another. And what happens then? Now, if it contains process 1 data, and after that it is just having process 2 data, then where that first process data which is stored in these registers. So during this context switching from process 1 to process 2, all the data which is present in this CPU register will be copied into, or you can say it is backed up. It is backup. It will have a backup in PCB. Okay, of that particular process in an area called context area. Okay, when you are switching from one process to another process, all the registers, as CPU is executing, CPU will have the data with respect to that particular process in these registers. Program counter, stack pointer, R0 to R15, everything will be with respect to that particular process. So when it is switching from process 1 to process 2, the content of these particular registers will be copied into an area called context area of the respective PCBs. Is it clear?
Yeah.
At starting, as if at all if no multiple processes are running, at that time this context area is empty. Context area is empty at starting only. Till you start switching. Once it switches from one process to another process, context area gets the contents of register, stack pointer, program counter. Okay. Is it clear?
Yeah.
Now, if you say priority based scheduler, which is preemptive priority based scheduler, here preemptive priority based scheduler. Now, here what happens in this particular round robin method, every process gets equal CPU time. But in preemptive priority based scheduler, what happens is CPU time is assigned based on the priority given to a process. Okay. Equal CPU time. Equal CPU time is round robin scheduler. Priority based scheduler, preemptive priority based scheduler is CPU time is assigned based on priority of that particular process. Now, where we use this? If we say round robin scheduler, generally it will be used in our desktop OS. Desktop OS or mobile OS or even embedded also. Embedded OS. All this uses round robin scheduler only. Preemptive is used in priority based scheduler is used in RTOS, real time operating system. Okay, because the priorities are given in your RTOS. Now if you want to make your Linux as suppose here Linux is using, by default this is using something like round robin scheduler, and if we replace this round robin by preemptive based scheduler, that time your Linux becomes RT Linux, which is real time Linux. Okay. Difference between this Linux and RT Linux is scheduler. RT is nothing but real time. Now, so whenever you are using something like priorities, if we say priority based, then the highest priority is given for interrupt handlers in any controller. In any controller, the highest priority is given to interrupt handlers. Then our normal task. The highest priority is given for interrupt handlers, and then our normal tasks are executed. What are these interrupt handlers? Interrupt handlers are nothing but special functions which are with we are using interrupts for that. These are also nothing but functions only. We are writing some particular functions for interrupt. Those are interrupt handlers. Okay. And other thing you give priority is for blocking calls. No, actually it's not priority, but blocking calls give you preemption. Okay, how I will say you that? Now, if we say, till now it is clear, right? Because if we want to understand threads, we need to understand. When you are using process, when you are executing process, what happens? Now suppose I am using a blocking call called scanf. Okay, and my CPU time scheduled is around 200 milliseconds. Okay, scanf I have called at 40th millisecond. So scanf is one some blocking call I have given in my process, and my CPU time allocated is 200 milliseconds. So scanf is called when CPU is executing at 40th millisecond. Right? Now what happens? Still I receive some input from my blocking call, that is externally. If at all, if the CPU time expires, so I'll be wasting 160 milliseconds of time. If I don't receive any input within these 160 milliseconds, at that time 160 milliseconds of time is wasted. And then it will move to next task. Right. So here what happens? So this is one disadvantage of process. It's one of the, you can say, limitation, not disadvantage, but it's a limitation with the process. So generally what happens when this blocking call happens, at that time that particular process goes into waiting queue. So as soon as you encounter a scanf or any blocking call, the processor shifts its operation and it shifts to the waiting queue, and then the process starts executing from the next call available. And when it will wake up again, it will wake up when the process comes out of the blocking call. Okay, so here the limitation is, even though we have 200 milliseconds of time is assigned to our process, after using this 40 milliseconds, 160 milliseconds are not exactly utilized by our CPU. And after this 160 milliseconds, it is jumping to next process. Okay. So here, if suppose I have some app, or I have some particular application where it uses some input, like my program is something like this, main. Then I have scanf option. That means blocking call. And then we have something like device read, device write, and the status of the device I want to see. So device status. So these are the operations I want to perform. Now, once the blocking call blocks this, then we are not able to execute these three particular functions. So we will not be able to execute this whole program till I come out of this blocking state. Okay, so even though I have tasks to perform in our process, still we are not able to utilize, and our CPU is free for 160 milliseconds of time, we are not able to utilize it. Here comes thread. Okay, here comes your threads. Basically, threads were created to utilize this particular 160 milliseconds of time.
Okay.
Here threads come into picture. So here, what is this thread actually? Every program, actually every process by default has a thread, and which is your main thread. Now, like process, we have a mechanism that permits an application to perform multiple tasks concurrently. Okay. So here what happens, it's nothing but it is also sequential execution of instructions only. Here what happens, so it is a mechanism that permits application to perform multiple tasks concurrently. Here a single process can have multiple threads, and all these threads are running concurrently and independently. And moreover, they share same global memory, initialized data, uninitialized data, heap segment, everything is same here. Okay. So here if you have multiprocessor system, at that time this multiple threads can run parallelly also. So if I have something like 4 cores, quad core you say or dual core you say, if you have dual core and if I have 2 threads, at that time both the threads will run concurrently on 2 cores. Okay, and moreover the limitation, like if at all if blocking call is there, so if one thread has encountered one blocking call, still the other is eligible to execute. Okay, so here we have some 1 second, how it will be I'll show you, or where it will have its memory. Now if you see here, this is our a.out file, and we know that here you will have text section, here you will have your what is it, BSS data, then you will have here you will have your RV argument, and here you have stack, right? And we know that we have seen we have something like shared memory which is allocated in between this particular area, right? Here we have shared memory also. Now when you create threads, so here the memory will be allocated for these threads in this area only. So here the stack will be there for stack for thread 1, stack for thread 2, stack for thread 3. Like this, here the memories will be created. Thread 2, thread 3. This is a.out file. Okay. And the program, obviously, the code will be here only in this code section. So basically, thread is nothing but a mechanism that permits an application to perform multiple tasks. Now if you see here, it is not saying about multiple process. Okay, within a process it is allowing multiple tasks to perform concurrently. That means here my read, write as well as this status can be run concurrently. Okay, now here that means a process can have multiple threads. Even the main program or main process is also a thread. So one thread is definitely there in our process, and that is main thread, and rest of the functions we can call it as multiple threads. So a process can have by default only one thread, but a process can have multiple threads. Now, why we need this? One of the limitations why we need to use this. Now, if you see process, what happens now when you are using some, suppose you are using 3 or 4 processes and you want to share the data in between the process. So what happens, even if you see a parent as well as child in a process, suppose you take only one process and if you see parent or child and if you take different processes, then what happens, it is very difficult to share the memory because they will have different PCBs for them or different areas where you're not sharing all the data directly. So if we want to do that, inter-process communication becomes difficult, and that is one limitation of your process. And moreover, when you are using code to create a process at that time, what happens? It uses something like copy on write, so it will have to copy or duplicate the whole system, and it takes time. That's why there is a limitation for this. So these limitations are overcome by these threads. So sharing information within threads becomes very easy. You have some techniques to be used here also. Why there will be some problem like if you are using multiple threads at that time, that multiple threads want to access the same variable. At that time problem will come, so that problems can be solved with some other technique. So as of now, we can just say that sharing information between the threads is quite easy than sharing the information between your process. Okay, and moreover, thread creation is faster than process. So these limitations can be overcome by this particular thread. Now, from system point of view, what we have, we can visualize that from user point of view, what we will, functions are nothing but some multiple statements, right, enclosed within curly braces. If we see one function, what we see, this is our main function. Here it will start from here to curly braces and end with this particular thing. So here enclosed between these two braces, whatever is there is our function basic. From system point of view, function is nothing but multiple instructions. Okay. Now every thread should have an entry point. Every thread should have an entry point from where the execution has to start. Why? Because we are running the threads concurrently. That means even we are running the threads concurrently, at that time, every thread to run independently, there has to be one entry point first. Okay, that entry point is like if you say main thread. At that time, what happens? Main thread will start from, if you say main, at that time main starts from main function. Main is entry point by default. So main, so here what happens? This main executes for suppose 100 milliseconds of time. Okay, and context, the info regarding this will be stored in PCB context area. Next, what happens if I have a new thread? The new thread entry point is nothing but suppose thread function. Thread function is my entry point, and this thread function we have 200 milliseconds. From there, we are saying that we have 200 milliseconds allotted for one process. So in this process, the main process is taking 100. Main thread is taking 100 milliseconds, and the new thread we created will take the rest of the 100 milliseconds of time. 100 milliseconds, and this 200 milliseconds, and the area and the data will be stored in stack area. Just now I have shown you. It will be like thread 1 stack, thread 2 stack. So here the data with this particular thread will be there in stack area and not in context area. In this way, the 200 milliseconds of your CPU time is utilized rather than wasting that particular 160 milliseconds of time. Okay. So, do we have some function to create this particular thread? Yes. We have some functions to create this thread, and that thread function is pthread underscore create. So here this belongs to POSIX library, and that's why we are writing P here. This is okay. What is this? I'll say you. So first of all, this is your pthread create, and this is library. This is there in some library. This is a library call. Okay. Now, if you remember, we have some function called printf, which is internally calling. Right. If you say scanf, it is internally calling your read function. If you say malloc, it will call some brk or sbrk. We have to discuss this brk or sbrk. I'll discuss that. All these three belongs to C library. Okay. All this belongs to C library. These are all C standard libraries. Library function. Okay. Then you say pthread. Internally, it calls a system call called clone, and this belongs to POSIX library. That's why we are writing there P. So P indicates POSIX library. Now here, if we want to see this, how to find out the library, we will see that. So here, what does this pthread? How to create this pthread? So pthread accepts some arguments. What are those arguments? Is pthread underscore create. Here, the first argument is ampersand thread. I'll just write it first. Null. Now, this is my thread function. So what are all these things? So first is your ampersand ti. Here ti is nothing but your thread identifier. Okay, what we said, we can have multiple threads. So here it should understand that which thread you are mentioning. So here if a unique name or this is a unique variable. It is empty starting, but it is a unique variable type pthread. It is of type pthread. Type is pthread underscore t. Okay, and every thread identifier will be unique. So no two threads will have same identifier. So it is easy for it to differentiate between which thread has been called, or you can easily understand by using this identifier that which thread is mentioned or executing or anything. So this mentions the thread identifier. Next is your thread function null. Null is nothing but here you will mention flags. If there are any flags used, then that flag has to be mentioned here. Flag. Next is your flag. I'll just write it here. Flags. And then you have thread functions. So what are these thread functions? Thread functions are nothing but thread functions are entry point. Entry point of base address. Entry point to access the base address. Entry point of base address. Base address of what? Base address of this hello. This hello's base address will be copied into this thread function. Okay. And then the last one, hello. Hello is nothing but an argument. It is an argument to thread entry point. Like we are passing RC, RB, like that here, this is our entry point for your thread. So when you call this pthread create, internally it will call a system call called clone and in user space of RAM, but again in kernel space of RAM it is using something called sysclone. Pthread create will use a system call called clone, and internally this will call sysclone in kernel space of RAM. All these thread information also be stored in PCB. Okay. Now, what is the functions of these pthread library? Functionalities or responsibilities of this pthread library is first to create or destroy the thread. Second, it is scheduling the thread, user space thread. And third is handle synchronization between your threads. Okay, so these are the functions or functionalities of your pthread create function. So, sorry, not function, because pthread create is only creating. Destroying, scheduling, handling is done by some other function, which is pthread library. So all this is done by your pthread library. Now, if I want to see, just with this, I'll just say, if we want to see some libraries, that which function is using which library, how to find that out? Now if I want to find it out, at that time here in this I have some list, and here a dot out is the last process executed, which is I think process a dot c. Okay. Now if I want to find out what are the libraries used in this, so we can use one command called LDD. LDD a dot out. So here what will be the output? If you see here, it will show you some lines of code, which is nothing but here you can see that it is using libc.so.6. Okay, so here you can find out that libraries. So if libraries in the sense which libraries are used to create this particular program will be shown, and the path is also shown. So the path you can see is library x86_64, line is gnu lib.so.6. So here the path as well as the number of libraries used, everything will be mentioned by, we can see that by using this particular command. Okay. Now we'll just write a program related to this thread. Thread1.c. Okay. Thread will accept only one argument. Okay. And at entry point. At entry point, it will accept only one argument. So first of all, we will have to just to start with this fashion view. Next, here I'll write my function. First I'll write my main function. In. Now, I'm taking one variable of type pthread_t, which is pi, thread identifier, and I'm taking one more variable, something like n. Now, then here we have pthread create. So here I will have to pass. So I'm passing the address of ti space. I'm not passing any flag. So here you will have null. Next, the name of the function. So here we give a name of the function as thread function. So thread_function, and then we are passing this hello only. Okay. So we will pass this hello. So here we created this pthread, and then to terminate a thread, we use a function called pthread join. Okay. So the purpose of this pthread join takes two purposes. One is to terminate a process, and other is to join a process. Both will be worked with the same pthread join. So here we are using it to terminate. So here we will pass this ti and the other variable which we used, and this ends our function. Now we will write the function for our pthread create. So here we are taking this as void pointer thread function. We have given thread_function as the name, and then we are passing it like void pointer arg. Okay. Now here what it will have the base address of hello. It will take the base address of hello as the base address here. Whatever the address of this hello is, the base address of hello will be passed as an argument to thread function. Okay. Now we will have to print it. So for that, what we are taking is, we are doing something like char. We are taking one pointer called string, and then we are passing the address of this to you from your pointer to char r. Okay. Now your string also contains the same address as your argument, and we are simply printing it. Printer percentile s slash n, comma, what we are printing is string. That's it. And we are using one more function here called return. String length of this string. So we are returning the length of the string here, which is nothing but 5, right? Now what it will execute and how it will execute, we will see. First of all, we need to add some libraries. So we will see which libraries has to be added. This is red1.c. So here, so as we have not included any library, that's why it is saying that pthread underscore t is not any unknown type. Okay, and we have to include this string.h also. Right? Other than that, so we will have to use this. Now we will add the library. So string.h, and the other one is your pthread.h. So here what exactly warnings we are getting is, you don't have any errors. Okay, size, then assignment to char, warnings, size. Okay, fine. Okay, so here we can now execute this /a.out. No such file or directory. Oh, sorry. Read. Okay, so here it is not executing, so we have to see why it is not executing. There is an error, sorry, I didn't see. Return one exit status. So there is one error called returned one exit status undefined reference to pthread join. So what this error is, So here we will pass null, otherwise and we will see. Here we will pass this as null once and we will just check. We will not pass anything here and whether this works or not. Still the error exists. Undefined reference to pthread create. Here also the error is in function thread function constant. There is a this is okay. Warnings are okay, but here the error is one exit statement. Undefined reference. Undefined reference. We have defined the reference pthread underscore t, ti, n, pthread underscore create, ti, null thread underscore function, hello, pthread underscore join, ti, comma, we are saying null, and here we are saying void pointer string. We are just simply passing this argument, printing it. That's it. Then why it is showing? Undefined reference. Okay. So here when you are declaring pthread function, we will have to use along with gcc thread1.c, we will have to use even pthread also, such that it will link those particular libraries. Because this is not only C library, it is using POSIX library also. That's why /a.out segmentation fault, and now we will just find out LDD a.out whether what is the libraries it is using. So here if we see, it is using the libraries called libthread.so and libc.so. That means it is using both the libraries, POSIX library as well as C library. So segmentation fault we got because it is trying to access an restricted area of memory. So we will have to check with this program that what is wrong with this. I'll just check it out and I'll say you. Then the other thing we have is okay. So here we need to know one thing. New thread entry point will never get invoked if the main thread terminates. That means if main program, if we see here, you can see that this is like a function, right? This is like a function, but it is a thread function, if you say. So this will not get invoked if this main thread is terminated, obviously, right? If the main thread terminates, then the new thread or thread function will never get invoked, and the entire process also gets terminated without completion. So always we will have to wait for the thread function to finish, and that we are doing it using, there we were using wait PID, but here we are using pthread join. Okay. So pthread join is used to, here you are using this as a blocking call. Okay. So here, if you see, the thread cannot be invoked when the main thread is terminated. But when you say process, even though the parent process terminates, child process will still continue, and that process we call it as orphan process, and the parent will be then init, right? So, but in thread it will not happen. In thread it will just terminate the whole program itself. Okay. Now here I have done some mistake, I think, in this program, and that's why we are not able to execute it. I'll just find it out and I'll just write it again, because right now I'm not able to see any problem with this. One more header file we will try to add, and we will see whether that works out or not. Okay, now what is the difference between these two statements? I'll say you. Here when you give this hash include within this particular operator, it will check this particular library in standard library. Okay, and if you say this particular thing in double quotes, it will check the current directory. Okay, this will be there in C directory and this will be there in current directory. So we have not included anything like that, and that's why we will not be able to find out that thing now. So here, shall I give it like pthread? So here we are returning something. So when we are returning something, we need to use that thing. N is equal to then no, I don't think. Okay, I'll just find out what is the error with it rather than wasting time. Without a cast. Okay, fine. There is no problem with that, but still I think I'll get that segmentation fault. Why I'm getting segmentation fault, I'll just have to find out. I'll just find that out. So we have some more functions related to this, like pthread detach is there. So p then we have some attributes also. So pthread attribute is there. So here, what is the main difference between thread versus process? So sharing, one of the things we have is sharing the data between the threads is easy than process. Okay, and thread creation is faster than process creation. These two are the main things. Even we have some disadvantages or limitation for threads also. So that process is like, if the termination of the main thread occurs, all the threads will be terminated. Okay, and if there is a bug in one thread, at that time it can damage all the threads. Okay, why? Because we are sharing the same address space and some shared data also. So actually here, as we are using the same data space or same address space, here if they are not isolated from one another, but if you say process are isolated, right? So they will have different memory, so will not have problem. But here, if at all, if a bug is there in one thread, they will, if they as they are using the same address space, all the threads can be damaged. Okay. And that's it. So we will have then how to use this threads with the now, as I said you, there is one more limitation, that if at all, if same data has to be, as they are all the threads are executing concurrently, there is a chance that I want to access the same data as some other thread. At that time, you will have to use some techniques. So what are those techniques and how to execute that, we will see tomorrow in thread synchronization.
Okay.
Okay. So till now, whatever it is there, it's clear, right?
Yes, yes.
So this program also, I'll just check it out. I don't see any errors in it, but still where it went wrong, I'll have to see why, because it's showing segmentation fault. So I'll just to say you that. So with this threads will be tomorrow. I'll just to finish this threads as well as memory allocation, and then we will have IPC mechanisms and signals after it, just to saying. So mostly by this weekend, I'll try to finish your complete course within this August month. So within this week, I'll just try to finish this. Actually, my goal was to complete it till this Tuesday only, but as we have not taken classes for these 2 days, that's why we are lagging. So mostly I'll just finish it by this weekend. Okay, then we will go with this embedded line. Okay.
Yeah.
So we will just end it for today. If you have any doubts, just to tell me.
No.
Okay.
Yeah.
Okay then. Bye. I'll just share this recording with you.
Oh,
And
thanks.
accidentally I have deleted 3 recordings. I'll just find out if I can just retry it, but I think as you have not able to download it, the 2 links which you shared me, I think that has been deleted accidentally by me. I'll just check that out once again.
Those 2 I have downloaded it. Again, it came, huh?
Okay, it came. Okay,
Yeah.
but still I have deleted 1 recording which I have not shared at all.
Okay.
In between 1 recording is there.
Okay.
Okay. Okay.
Yeah. Okay, thanks.
Bye.